All right, in section 4, you should have read that these are looking at dependent samples. Um, here's a problem number 3 that's talking about corn. So data below are yields for two different types of corn seed that were used on adjacent plots of lands. So the land that they're planting the corn in are roughly the same. They're right next to each other. They're getting the same amount of rain, probably the similar makeup. And so these things are paired up. This one pairs to this same adjacent plot of land. This is the same adjacent plot of land. I wouldn't want to compare the 2015 to the 2578 because that was a different land type. So that's why it's dependent. So if I wanted to create a 95% confidence interval for this, the data's in there. I'm looking at a t-stat. Instead of a 2 sample, I'm looking at a paired. There's my type 1 corn, type 2 corn. It'll make a difference column for me if I like, and it said a 95% confidence interval. So I get that information and I can just plug it in. 2 decimal places. And so again, what does this 95% confidence interval mean? Again, the differences between the two. Because of confidence, what does it suggest about Farmer Joe's claim that type 1 seed is better than type 2? Only includes positive value and does not include 0. That's not the case here. I have 0 in the mix. Since it includes 0, there is not sufficient evidence to support Farmer Joe's claim. So maybe the mean difference is 0, right? Because 0 could happen in here. And so that's why we are picking C. So this is the easy part of the question. This is the hard part, interpreting. All right, so now we have more dependent data, and we're going to do a hypothesis test. So Friday's on the 6th of the month, and Friday's on the following 13th of the same month. So again, we're dealing with the same month. We're dealing with Fridays. So this Friday is within the same month of a hospital. This is a different hospital. This is a different hospital, right? Are they different hospitals or different months? This is January, this is February, this is March, this is April. So the month are the things that makes them dependent. So I want to compare January's. I want to see if the differences between here are roughly the same or are they different. So be the mean of the differences, or the difference between the means. So differences between the means would be independent. The mean of the differences means I'm looking at a dependent sample. Null is always that it equals 0. Alternative, that they are not affected, so one's not greater than the other, so I would put not equal to. So Friday the 13th doesn't make anything bad happen. Let's see, let's find the test statistic. So again, I have the data in there. I'm looking at t-stats, and they are paired because they depend on one another. This one depends on this one. So I have from the 16th and from the 13th. We can save our differences if we like. And this is what my hypothesis test looks like. So I get a test statistic of negative 2.7 774 to 3 decimal places. And identifying the critical values. So in this one we could look at our calculator and our T calculator. Since our alpha is 0.05, I'm looking for a 95% between, right? And my degrees of freedom, if I have 1, 2, 3, 4, 5, 6 differences, then my degrees of freedom is 5. And I went 95% in between. So these should give me my critical values. So if my test statistic is beyond negative 2.5706 or above 2.5706, that puts me in a rejection region. So since I'm dealing with a not equal to problem, that's why I'm two-tailed. It'd be plus or minus 2.571. Now again, look at our p-value, 0.0392, that's less than our alpha. That would tell us to reject. Using the classical approach, negative 2.7, that's over here in the rejection region, that would tell me to reject. So either way, I'm getting a rejection. So there is sufficient evidence to warrant rejection of the claim of no effect. So sufficient evidence appear to be affected. Hospital mission appear to be affected. And that's because we're looking at dependent samples in this problem. Then usually at the end there's some wordy ones. Making sure we're comfortable. Assume that the paired sample data is represented and the differences. So they tell us it's paired. Sometimes it's tough determining if it's paired data or not. Are the heights of candidates who won elections and the heights of the candidates with the next highest number. So this was one particular election. This was a different election that was going on. Because again, on this one, the runner-up was taller. But looks like a lot of times that the winner is taller. Maybe the taller, the more power they seem to have. But each race, election race, that's what matches them up and make it a paired t-test.